left off right here, and I think in all three classes we got to kind of the same points where they're talking through what these functions represent, and then here's how cost works as a sort of as it relates to revenue and profit, and then I said go finish this, right? Okay. And time has passed. We're in the future now, so you went and finished it. How do we find a cost function if we know profit and revenue? Subtract. Subtract which way? Revenue minus profit. Okay, so if we do that, 150x, 250x minus 150x minus 750. What do you get? 100x plus 750. Okay, so that's going to model the weekly cost or the expenses for this shop when they sell X bikes. If you want to kind of get into breaking down what this thing tells me, there are two pieces here, right? Two terms. One of them is fixed, $750. The other one is variable, it changes with X, right? This fixed cost, that's the stuff that happens no matter what, right? That's paying rent and utilities and stuff like that that doesn't really have anything to do with how much business they did. The other part, the variable part of this, 100 times X, well, if X is the number of bikes they sold, then this is probably, this 100 times X, that bike people would cost $100 to like actually get out. Right? So there's this fixed component and variable component to these, and you can see that show up in the other two equations as well, right? The fixed part and the variable part. If you look at the profit, minus 750, well, that's this plus 750 that showed up here, right? It's the same money. That money that you're paying for rents and whatever, that comes out of your profit or it contributes to your expenses. Right? So that's why I showed it up in both places. Okay, but we've got a cost function now. We've combined these things. So now I have something that I can just, plug an X value into and it'll tell me, what the expenses were. So what is C of 10? Everybody agree? Just plug 10 in here, right? You get 1,000 plus 750, so 1,750. More importantly, though, what does that tell us? Okay, how much the expenses were? When? When you sell 10 bikes. So anytime I ask you to explain what a point represents or something like that, what I'm looking for is you to tell me what these two numbers mean, right? This is an ordered pair on a graph, if you want to think about it that way. It's an X and a Y that go together. But we've got a context for what these things mean set up by the problem. So explaining what it represents is, hey, give me a sentence that has those two pieces of information and how they relate to one another. So explain what this point represents for Mike's bikes. Something like the shop's total weekly cost is $1,750 when they sell 10 bikes. Something along those lines that, again, is showing, like, that I know what the units are, right? This is dollars, this is bikes. It's dollars specifically that represent the cost of the expenses, and here's how they're related to each other, right? Something along those lines. On something like, if this was a test question and this, kind of two things was worth, I don't know, 10 points, this would probably be like 3 or 4 of them maybe, because I expect that you can plug something into a function and crank out an answer, right? So like, it's worth some points, but not a lot. Explaining is the kind of higher level thinking skill that we need to be doing, right? What does that function P of 2. There's P of X, plug in 2. What do you get? Negative 400. Negative 450, sorry. Which means I may have done that wrong this morning. I have to go check that before I post the message. Yeah, negative 450 because 150 times 2 is 300. 300 minus 750 is 450. What does that mean? Profit when they sell 2 bikes. Okay, but it's negative. They lost money. Yeah, profit can be negative. It means things aren't going the way you wish they would, right? But it happens. P of 2 is 150 times 2 minus 750. So 300 minus 750, which is negative 450. Profit when they sell 2 bikes is negative $450. Again, meaning they're in the red. Which I guess we're sad about if we're putting ourselves in the position of the bike shop, or maybe happy about if they're the crosstown rival that we don't like very much. But they lost money. That's what happened. Okay, which begs the question then, how many bikes do they need to sell in a week in order to break even? What? I don't know. Why 5? Okay, so what does it mean to break even? You don't make money, but you don't lose it either. Okay, so break even. Another way to say that would be that your profit is 0. Another way to say that you don't make money, but you don't lose any either, would be that your cost is the same as your revenue. We have functions, so equations basically, for each of those 3 things, so there are a few different ways we can go about figuring this out. 2 is too few because they lost money. 10, well, the cost is 1750. The profit when they sell 10 is positive 750, I think. I don't know. Yeah, 750. So it's fewer than that, right? So it's somewhere between 2 and 10. To get that dialed in more, we can take the profit and set it equal to 0. So yes, x is 5. So that's bare minimum they need to do in a week to, make it worthwhile to even be there, right? Okay. Did you have any questions about that? Okay. All right, so there's a way, there's an application where we can, use this idea of how we combine functions together, right? I had revenue and profit given. I can use that to find cost. If I have any 2 of these, I can find the third one by just sort of taking this and rearranging. Don't treat that as like a formula to memorize or something, though. The way these things are related, just think about what the terms mean, right? Cost, revenue, profit, and I think you'll be able to see how it should go through. Okay, so recap yesterday, we talked about function arithmetic. Add, subtract, multiply, divide, 2 functions together, and what happens when you do that. We did that analytically using the symbolic version of the functions. We did it looking at a graph. You can do it using any other representation of a function from a table or whatever else. And then we looked at this application involving sort of businessy kind of things. Today we're going to talk about the other way we can combine functions together, which is function composition. So this example 4, this is a problem that, we just encounter all the time, sort of out in the world, but maybe haven't thought about that much before. So let's take 5 minutes. Y'all work on that, see what you come up with. Wonderful. That's okay. So how much is this pair of super cool, apparently transparent Chuck Taylors going to cost us? 42.50. 42.50 maybe. Okay. If we do the discount first, so the question was, they're on sale for 25% off, and you have a coupon for an additional $10 off. Final sale price, how do you find it? And then does anything change if we switch the order? So let's first go with discount happens first, then $10 off. How do we do it? Okay. Okay. So 70 times 0.25, what are we doing there? Taking 25% off, right? I mean, really what we did is figure out what 25% is, and then we need to do 70 minus 17.5 to get 52.5, right? Okay, so that's the discounted price. That's what, any Yahoo off the street is going to pay because they're on sale, right? You can also do that by taking 70 times 0.75, right? And get there directly. It's 25% off. Okay, so you pay 75% of the price then. That gets you to the same place. Everybody's okay with this? Right? This isn't, new to anybody? Okay. Okay, so we know how to do that. Then the additional $10 off, what do we do? And that part's important, that we don't start back over at 70, right? We take this and subtract 10 and get our 42.5, and there's your answer, right? Switch that out for an exclamation point. Okay, so 25% off, we figure out what 25% is, we take that away, right? Or is directly 75%. And then an additional flat $10 off to subtract, but again, the important part is that we subtract from here, from this sort of intermediate step, not from all the way back into the beginning, right? Do you agree? Okay. Now, what happens if we switch the order of those? Yeah, we end up paying more. Other order, how much do you end up paying? 70 minus 10 is 60, and then 60, 25% off is 45. Okay, so it matters. And now if you weren't already a person who thought about the way coupons and things stack, now you get to be part of the club of people who are like, which way do they stack though? Like, which order does it happen in? Because it matters. It doesn't matter if they're both percentages. It matters if one is a, subtracting a flat rate. But the point though is that it does matter. It does make a difference. What we're doing here, and in either case, what we're doing here is an example of function composition. A function is some kind of process or operation by which we take some value and turn it into some other value, right? Or pair it with something, see how they kind of relate to each other. We've done two of those here. One was the take 25% off thing. Now, taking 25% off, depending on how we did it, that might have been in two steps, but think of it as one operation, right? One thing that's happening is doing 25% off. The other one that we did is taking $10 off. That one, just a single step, kind of no matter how we do it. But again, two big operations going on. Composition means, okay, take two or more functions, two operations like this, and do them one after the other, but sequentially. What do I mean by sequentially? I started with this, I did this, then I did this, and then that gave me my final answer, right? But the kind of middle part of that, I did this with a highlighter thing, so I can't, take my hand off of it. This middle part, now my hand is just sort of, got some kind of thing happening, I don't know. This middle part, we go directly from one into the other one, right? I didn't jump back to 70, to the price I started with. I used the value I got after doing the first kind of process to do the second one, and then that gave me the answer, right? Okay, that's how composition works. You do one, and then you do the other one. Another example, and I use this in the video as well, but I like it, so let's talk about it again. Doing laundry, two big things that have to happen, right? First, we got to wash the stuff, then we got to dry the stuff. Whether that's, in a washer or in a sink or one of those old-timey thingies down in the creek, you got to wash it somehow, and then you got to dry it, again, whether that's a dryer or a clothesline or whatever. I would put folding there as well, but like sometimes that part doesn't necessarily happen on the same kind of timeline, at least in my house. There's just a bag of clean clothes of shame in the corner that I didn't quite get to. The way the thing works is that we start with what? Okay? And what do you put in the washer? What kind of clothes? Washer does its thing, right? Rinse, spin, all that kind of stuff. Does its thing. What comes out of the washer? Yep. Wet, clean clothes. Dryer does its thing. It goes off, but you're not quite ready to get them out and face the reality of folding them yet. So you just go ahead and put it on for another 10 minutes, right? It's okay. We've all been there. You can admit it. Then what? Dry clean clothes. Okay. I like this example for two reasons. One, does it matter which order you do those things in? Boy, it sure does, right? You put your dirty clothes in the dryer, but no, like, first of all, like I've got kids that are this big, so like everything's got food on it and like dirt and whatever. So like hot, dirty clothes is not a situation that I want to get into. And then you put them in the washer, and like you don't really end up where you wanted to be. So the order is very important. And again, it shows us that these things happen in sequence, right? What did I start with? My initial input, dirty clothes. Okay, well, when we're working with, algebra, like math classes, the big things, our initial input's going to be some x value, right? Some thing that we given in the first place. One function does its thing, but it changes that into some different thing, and then that changed thing is what becomes the input for the second function, right? They happen in sequence one after the other. And again, the order matters. And then once we've kind of got the idea of how I string those things together, I don't say, oh, it's Saturday afternoon, I better go do the washer and then the dryer. I say, oh, it's Saturday afternoon, I better go do the laundry, right? I sort of combine them into one idea that encapsulates all of this stuff that's going to happen. Does that make sense? That's what composition is. When we create a composed function, which I'll show you what the notation looks like in a second, but when we compose two functions and create a new one, what we're doing is encapsulating the idea of taking those two separate processes and combining them into one that happens one after the other in a particular order, and just thinking of that as one thing, right? Just like doing laundry is one thing, I don't specify this and this and this. Yeah? Okay, that's composition. The way we write composition looks like this. It's a new operation. It's a thing that we haven't done in other places. So it gets its own, name, its own symbol or operator to show us that we're going to do it. This little circle is the composition operator. If you want, you can read it like of. In the same sense we use of to talk about functions, right? So when we write this and read it f of x, what that means is, hey, I have a function that I'm calling f, and I'm going to write it down using x as the symbol or the placeholder, right? And then if I want f of 3, I just replace the x's with 3's and figure out what that looks like. So when we write f of g of x, what we mean is f of g of x. In other words, we're going to have a thing that looks like f, but anywhere f had an x before, I'm going to replace it with g of x. So the inner thing here is the thing that happens first. So that's the washer. The outer thing happens second. That's the dryer in the laundry example. Which means that f of g is different than g of x. Right? This would be switching the order, which, in the laundry example means bad stuff is going to happen. In general, means different stuff is going to happen. Right? The outcome is going to change, just like with the shoe thing. Okay. Okay. So if it has a 3, then we're not looking at it, we're not going to be writing a thing that's in terms of x anymore. Our final answer is just going to be a number. And what we want to do is start by finding g of 3. So for this particular example, what's g if I let x be 3? 10. Plug 3 into g, you get 3 plus 7, so that's 10. 10 is my pile of wet clothes that need to be dried. So I plug 10 into the remaining function, right? I like work my way out. What's left is f of 10. I can forget all about the fact that g ever existed at this point. All I'm doing is a function evaluation where I'm going to plug 10 into f. When you plug 10 into f, what do you get? 20. Okay. If we're doing that with a number, with a specific x value like this, then that's kind of how it goes. You plug into one, then you use that result, that like intermediate result, to plug into the other. Does everybody see how this is the same thing that we did with finding the price of the shoes? We've got an equation now instead of a like it's 25% off that we just kind of know from like being in the world how to do that, right? We've got a specific equation telling us what to do, but we're doing the same thing. Start with 3, do this, and then take whatever you get from doing this and plug it into this. I'm sorry, you explain why we started that. Like why we do G first? Yeah. So that's just that's how we set the notation. Yeah. So that's just a convention of like how the notation works. F of G means do G first. Okay. Yeah. So you kind of start, farthest to the whatever direction that is, right? And then work your way out. Yeah. So and this isn't limited to just doing 2 functions. You can do f of g of h, whatever, and you can do the same kind of thing here first, then here, then here, and just sort of work your way out. Yeah. 1, 2. Yeah. So that part's not for a reason so much as there is an order, and here's how we express that in the way we write it. Okay, so there are three others there where you're doing the same kind of thing. The next one with a specific x value, so for one. The last two for a variable. So now doing this with a variable, it's the same idea. You take one and plug it into the other, but it's a little bit more like you're, like the laundry method, like encapsulating both processes like you're making one formula instead of both jobs. So again, let's take 5, 7 minutes, something like that. You guys give those three a shot. Okay. So g of f of 1 means we need to find first f of 1. What's f of 1? 4. Plug 1 in here. 1 squared plus 3 times 1 is 4. Okay, so we hang on to 4, and then we go do another function evaluation. Right? We plug 4 into g. When you plug 4 into g, what do you get? 7. So it's 7. Okay? All right. Now g of f of x. Let me actually go over here so I have some more room. F is 7x plus 1. G is x squared minus 5. Okay. I talked to several of you about this, kind of individually, but just as a reminder about, function notation and how we use it, try not to get hung up on, there's an x here and an x there, and x is all over the place. What we're using that for is just a placeholder for something else that we're going to fill in. So when we say that g of x is x squared minus 5, what we really mean is the g of anything is that same thing squared minus 5, right? Whether it's x or 17 or some other function or whatever we're going to feed into it, you square that thing and then you subtract 5 from it. So if what we're trying to find, like in C, is g of f of x, and that means g of, oh wait, hang on, sorry. Got my coloring scheme backwards here. That means find g of f of x. What that means is we're going to have a thing that looks like g, and g looks like this, and we're going to fill it in with whatever f is. Well, what f is 7x plus 1. So that's 7x plus 1 squared as a quantity minus 5. Now I dropped the switching between the colors thing because now I've gone from this kind of abstract thing about how this was coming in to a concrete algebraic expression that now we can start to simplify. Okay, is everybody okay with how I did the composition? It's g of f, so it's going to look like g. Well, here's what g looks like, but made up of f. That's what this says. We've done the composition, then what's left is that there's some algebra kind of staring at us, daring us to simplify it. What's 7x plus 1 squared? Okay. Good. 7x twice. Can you expand this? So the outer and inner parts would be 1 times 7x, and then 1 times 7x again.
Got it? Okay, so first, outer, inner, last, right? Everybody multiplies by everybody else. 49x squared, 7x, 7x again, and then 1. And then combine those. Okay, part D is going to be very similar. I'll leave that for you. We can, check in on Thursday and make sure we're on the same page there. Let's look real quick at how we would do this graphically. We have F, we have G. F I recognize, it's a straight line. G, I don't know. Maybe if you took trig in high school, you know what G is, but it's not a function type that we recognize probably, which means that we can't go find an equation for it and do things that way, which must mean that everything we need is sitting there in the graph, right? Okay. If I don't know how to, figure out what this thing is, then everything I need must be in this picture somewhere. Okay, f of g for x equals 2. What's g of 2? Find 2, find g. G of 2 is the y value that goes with it, which is negative 2. Okay, then what? Now you find what x value? Wait, I can't tell if you're saying f or x. Okay, f, right, okay. F's x value is a very confusing sort of thing to hear, yes. Okay, so the x value that we have is negative 2. And what we want to do is look up what the function called f does for negative 2, right? Okay. So here's negative 2. Here's f. So final answer is negative 4. Hopefully that has a similar sort of feel to what we did, above with taking the two functions at like symbolic, like equation versions, right? You plug in and then you plug in again, but you don't start over. You plug in and then keep that middle thing. That's what we did here. You plug in. Okay, well, graph, that means looking up. So we go look up that value, bring it back with us, and then we go plug in again, but using that intermediate step, right? Here you do the same thing. You just use G both times. And here you start with that one. So I guess 3 then that we didn't do, this and this and this. Make sure to finish those. Do those for Thursday. You should be in good shape to do the homework over, function arithmetic and function composition. Thursday we'll talk about inverses and what that means. It's kind of an extension of this. Yeah, so get started on the homework if you haven't already. Keep track of stuff you want to talk about, or feel free to send me emails or come by office hours. Otherwise, I will see you guys on Thursday. Have a good day.